In this video, we will continue with the maximum likelihood derivations for psi naught, starting from the concentrated log likelihood that we derived in the previous video. And I recopy that over here on the slide. Remember, we want to look for the MLE of psi naught, subject here to the restrictions that psi naught has a reduced rank H, namely the cointegration rank, such that it can be decomposed in terms of two low rank matrices alpha and beta. And if we have a closer look at the log likelihood, then again, we recognize here some form of squared residuals. Now, what is the multivariate regression model that is corresponding here to these residuals? Well, we seem to have the U hats as the responses and the V hats as the predictors, and psi naught is the parameter in this multivariate regression. Now, it is not a regular multivariate regression, but it is a special one, where we impose this additional constraint on the parameter psi naught, namely that it has reduced rank H. And so this is indeed the log likelihood that corresponds to a so-called reduced rank regression model. So now that we know this, the next question is, how do we obtain the maximum likelihood estimates for alpha and beta? To arrive at their MLEs, well, we are again going to break up our problem into two sub-problems. First, how would you estimate alpha if beta would just simply be given to you? Well, then alpha could just be obtained from regressing U hat on the predictor beta prime times V hat. And that is indeed correct. So we have here our expression for alpha, the estimator of alpha in terms of beta, as written down here on the slide, and you just recognize the least squares formula. Now I can also re-express the estimator for alpha through these sample variance covariance matrices as defined here at the bottom of the slide. And these will actually be useful for our further derivations. Now, just like we obtained the maximum likelihood estimator for alpha, we also have our estimator for omega in terms of beta. This is nothing more than the average sum of squared residuals from the same regression, namely of U hat on beta prime V hat. Now I do some rewriting over here to also arrive at this final expression in terms of the sample covariance matrices. Now, what are the details? From the first to the second line, I just expand the squared term, which gives me the squared term for the U hats. Were taken together with this factor 1 over t. This immediately gives me here the sample covariance matrix of the U's. As the last term, I have the squared term in alpha beta prime V hat, where the sample covariance matrix of the V hats is popping up. And in the middle term, I have the cross terms where the sample covariance matrices of VU and UV are appearing. In the third line, I regroup the terms involving this blue guy over here, namely alpha hat times beta prime, which gives here this first term in parentheses coming from this guy. And then I have the second term in parentheses coming from this guy over here. And I bring this term then just simply to the end. How do I arrive at the last line? Well, I've put a box around alpha hat. Since I plug in here in the third to the fourth line, the expression of alpha hat given at the corresponding box at the top of the slide. And so just plugging in the expression for alpha hat in this box will finally make us end up with the last line, since quite a lot of terms cancel out. But to see what is going on here, I actually needed an extra slide to verify all of the calculations. And that's what I do on this slide. So I recopied over line 3 from the previous slide. And then I plug in the expression of alpha hat in the box. That is then the second line. To arrive at the third line, I work out this product over here. Okay, so that brings me at this long expression, this guy over here, first times the sample covariance matrix of VU, so that it's this term. And then I have this long expression over here, times the second term in parentheses, which gives me this long expression. And so that last term is copied over on this line. Now things will start to simplify as of now. First, look at the terms in red over here. They actually just cancel out to the identity matrix. And I'm only left then here with sigma hat UV times beta times alpha hat prime, which is this guy over here. But that guy is exactly the same as the last term here that I had already. So also these terms in red cancel out. And I'm left with my final expression for omega hat. Now let's take a minute over here to see what we have done. We have obtained the estimators for alpha and for omega from a least squares regression of the U hats on beta prime V hat. Now in a final step, we concentrate the log likelihood further and plug in the maximum likelihood estimators for alpha and omega. And to arrive at this concentrated log likelihood for beta only, I have here the details on these lines. First, I just bring in the first line the decomposition of psi naught in terms of alpha and beta. And I immediately insert the NLE for alpha. In the second line, I then also bring in the expression for the maximum likelihood estimator of omega hat in red. But be careful, we actually need its inverse over here, which you can take outside of the log determinant in front of it by changing this plus sign into a minus sign. Now, as you can see, this blue term over here simplifies quite a bit, namely to t times n over 2. And I have included the details of the simplification at the bottom of the slide. So let's have a look at the derivation. And let's start just from the blue expression popping up over here. Since this is a scalar, I can bring in the trace function. And from its cyclic property of the trace, I know that I can move the first term all the way back to the end, and nothing changes, to arrive then at this expression, where I also immediately have taken out omega hat inverse outside of the sum, since it does not depend on t. But this expression over here, this expression of the squared residual, is exactly what is popping up in the definition of omega hat, verify that from the previous slides. So this squared sum is nothing more than t times omega hat. Okay, so I already arrived at this expression. Now I can also pull the inverse again all the way to the back. And then I have omega hat times omega hat inverse, which just simplifies to the identity matrix of dimension n. And so then I'm left with the trace of T times the identity matrix. And the trace is nothing more than the sum of the diagonal elements. So that further simplifies then just to n times T. All right, so we arrived at the final concentrated log likelihood, where we only need to solve still for beta. And there is one final trick that we need to use that involves the determinant of a matrix that can be decomposed in 4 subparts, because that will allow us to rewrite the log likelihood in this form. Now, the final trick itself is not so important, but you have all of the details here on the slide if you want to verify this. What is left for us to do is now maximize this log likelihood with respect to beta. And realize that it's only popping up in this last expression over here with a minus sign in front of it. So we can equivalently maximize the log likelihood by minimizing this expression over here. And that's also what I have rewritten on the next slide. Now, this is a very new expression to us, but we can simplify it a bit further. Remember, what does beta contain? Beta contains the co-integrating vectors. But the co-integrating vectors are not unique. Only the co-integration space was unique. So we can impose here this convenient normalization, namely that the denominator that is popping up over here would cancel out to the identity matrix. And then our minimization problem simplifies even further to this expression on the slide, where we minimize this objective function subject to the constraint that this guy, the denominator from the previous slide, is the identity matrix. Now, since this sample covariance matrix is positive definite, I can also rewrite this expression slightly in terms of a new parameter beta star, which is nothing more, let's say, than the square root of this matrix times beta. And I do all of this because then you can show that it turns out that this actually corresponds to a standard solution in multivariate analysis, where the columns of beta star are given by the eigenvectors corresponding to the h largest eigenvalues of the matrix that is popping up into our objective function. And the optimum value of the objective is then given here by the product of these terms where these h largest eigenvalues appear. And plugging this finally into the log likelihood where we had the log of this product, that boils down then to this expression where the sum of the logs appears. Now, we don't have time to go over all of these details, the derivations that are involved over here. But if you're interested in finding out more, I can recommend here this introduction textbook by Anderson. So instead, let us just have a look at an overview of all of the maximum likelihood estimators for the parameters that are involved. So we know that the maximum likelihood estimator for beta can be obtained from this eigenvalue decomposition. And then all the remaining maximum likelihood estimators can be expressed in terms of the estimator for beta. We arrived the MLE for alpha, the matrix of adjustment coefficients, as well as the MLE for the variance covariance matrix. And finally, the AR type of parameters can be simply obtained from this regression, where we have the series indifferences corrected for the cointegration relations as a response. Now we have all of the lagged differences popping up as the predictors. All right, so very good. Now all of these MLE derivations, we assumed that the cointegration rank was fixed at a value h, so that we have h cointegration relations. But the natural question to ask, of course, is how should we determine this cointegration rank in practice? And we will look at that in the next video.